In a previous video, we looked at the overview of the mass spectrometer instrument, and in this video we're going to take a little bit of a look at what this mass spectrum is going to look like. So we said in the previous video that we have our two axes. We have on the x-axis the mass to charge ratio, and this is represented as m over z, m being the mass, z being the charge. And on the y-axis of this mass spectrum, we would have the signal intensity. Okay, so some kind of count of the number of ions of that mass to charge. Now, while this might be often drawn with kind of straight lines representing single mass to charge ratios, the reality is that we still have kind of peak shapes to these different mass to charge ratios. So we might have peaks that look like this, next to one that looks like that, next to one that looks like that. Okay, so that might be some of the peaks. Now, just like we talked about with chromatography, where we would have resolution between analytes that we're eluting on a chromatogram, we can talk about the same kind of idea here, where we're looking at the difference between these two peaks, this kind of difference in mass to charge ratio. Okay, we would consider this the resolving power. And just like we would talk about resolution being the smallest difference between the two peaks that we can distinguish, okay, that same resolution kind of calculation that we would use for chromatograms, we can use here as well. And the resolving power we would dictate to mean the ability to separate two peaks with similar mass. So you would have the mass of one over the difference in mass. Okay, so this is the smallest difference in mass that can be detected. Okay, so we're often plotting these signal intensities, kind of looking at the y-axis here, as potentially either being the current, we might say they're the ion current, and we often plot these as a relative intensity, where the tallest peak is set to be 100%. And this is simply to allow for easy comparison one to another, from one peak to another. Okay, now I've drawn several peaks here, but this might actually represent a single pure substance. Now, let's think about why we might see several peaks. Okay. When I say mass, we have to consider what is the mass of a particular ion. So let's consider lead plus. Okay, so this is a singly charged lead ion. Now, if we're looking at the mass to charge of this ion, we have to consider that we need to know the mass and the charge. So if we have lead with a single charge versus lead with a double charge, the Z portion can be a +1 or +2 depending on what our charge is. And so where it shows up on the mass spectrum is going to be different whether the lead has a +1 charge or +2 charge, even if they are the same mass overall. So let's consider the mass of the ion. Now, there's a number of ways that we can speak about mass. We might be most familiar with the mass on the periodic table, which is the atomic mass. And if you recall from general chemistry, the atomic mass is a weighted average of all isotopes present. Now, the molecular mass would be the sum of all atomic masses for a molecule. So we might be considering that. Both the atomic mass and molecular mass would be what we would get from the periodic table. They're again weighted averages. Now, if we're looking at individual isotopes, we might see that, or might need to use some different terminology for single isotopes. So another type of mass we might talk about is the nominal mass, okay, which is really going to be related to a monoisotopic mass. So where atomic mass and molecular mass were related, the monoisotopic mass and nominal mass and exact mass, oh, let me put my sheet up there, exact mass are also kind of all related. Let's start with the monoisotopic mass. This is the exact mass of the most abundant isotope of the species. So it's not the weighted average, but just the most abundant isotope. Okay? And this is the exact mass. So what is the exact mass? Well, the exact mass is to many significant digits, or to many decimal places. We're getting very, very detailed numbers beyond just 1 or 2 decimal places. This might be up to 5 or 6 decimal places to get the exact mass. And you have to have a really strong resolving power in order to distinguish down to that level of saying this is this peak and not something else, not a different mass to charge ratio. But what's more common that we're working with low resolution mass spectrometers, or something that has a low resolving power, is the nominal mass. And this is simply the integer mass for a monoisotopic mass. Okay, so what does this mean? So if we go back to this example up here, we might have several different lead species. We might have the lead isotope that weighs 206. We might have lead 207, and we might have lead 208. Now, if you were to only look at the atomic mass, you'd see the weighted averages of these abundances. But here we're getting to see single isotopic masses, and depending on our resolving power, we may or may not be able to distinguish between these and get additional decimal places to go from the nominal mass of 206, 207, and 208 to more specific masses that have additional decimal places. So when we are looking at a mass spectrum, we have to remember that even though we might get multiple peaks, these might not represent different kinds of chemicals, right? We would consider this sample of lead to be a pure sample. It just has multiple isotopes present because of their naturally occurring abundances. And so when you see multiple peaks on a mass spectrum, unlike with a chromatogram, this does not always indicate a mixture of substances, right? We would have this series of isotope peaks here, and we would have another series of them further down that might be our doubly charged lead 2 plus 206, lead 2 plus 207, and lead 2 plus 208. And these would occur rather than being at 206, 207, and 208. Because the charge here is 2, now these would occur at 103, 103.5, and 104. Okay. So when you see multiple peaks, you have to consider if isotopes are present, as well as what the charge state might be. And looking at the difference between the masses of isotopes can help distinguish the charge state. Okay, we'll dive into a lot more about what other peaks we might get and what happens when we're seeing peaks that are not simply representative of isotopes, but are actually from the molecule, a larger molecule, kind of falling apart into pieces. So we'll look at how we interpret a lot of that in a later video. But for now, consider this your introduction to a mass spectrum, where you're looking at isotopes, the ratio between them in terms of their natural abundance, which is going to be represented by their intensity, and considering how the resolving power is important for distinguishing one isotope or one peak from another.